Out there, in the cold, dark expanse, where the sun's breath finally fades, there is a profound silence. It is not a silence of nothingness, but a quiet transition. A cosmic threshold, where one kingdom ends, and another, vastly larger, begins. A tiny, tenacious explorer from Earth has crossed this boundary and sent back a message. This message, carried on the faintest of radio waves, doesn't speak of grand explosions or cataclysmic events. Instead, it tells a story of subtle shifts and a newfound quiet, a whisper from beyond our familiar solar shores. So, what is this remarkable machine, this cosmic emissary named Voyager 2? In simple terms, it is a robotic space probe, a marvel of 1970s engineering, built by human hands, launched by human ambition. It is a semi-autonomous scientist, packed with instruments, designed to see, to feel, to listen. On August 20, 1977, before its twin, Voyager 1, it lifted off from Cape Canaveral, Florida, embarking on a grand tour of our solar system's outer giants. Voyager 2 is not large. Its main body is about the size of a small car, with a 3.7-meter dish pointed toward a tiny blue dot, Earth. Power comes not from solar panels but from a radioisotope thermoelectric generator, using the natural decay of plutonium-238 to produce heat, converted into electricity. This long-lasting power source is the heart of the spacecraft, allowing it to journey and communicate for decades. It flew past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989, revealing storms, bizarre moons, and intricate rings. After its final planetary encounter, the primary mission was complete, but the journey was far from over. NASA set a new goal, the Voyager interstellar mission, to sample the space between the stars and keep talking for as long as it could. To understand Voyager 2's breakthrough, we must first understand the neighborhood it just left. Our sun is an active churning star, constantly spewing a torrent of charged particles, the solar wind, rushing outward at hundreds of kilometers per second. This wind travels beyond the planets, inflating a gigantic magnetic bubble, the Heliosphere, our sun's domain, our cosmic cocoon. Imagine the Heliosphere as a ship's wake moving through the water of the interstellar medium. Gas, dust, and cosmic rays. As the sun moves, its wind pushes against this medium, creating a boundary. First, the termination shock where the wind slows. Beyond it, a turbulent heliosheath. At the very edge lies the heliopause, not a wall, but a boundary, likely just tens of thousands of kilometers thick on a cosmic scale. It is where the sun's magnetic influence ends and the galactic field takes over. Inside, you're bathed in solar particles and shielded by solar magnetism. Cross the heliopause, you are truly in interstellar space. This bubble protects life on Earth, deflecting a significant portion of high-energy galactic cosmic rays from distant supernova and other violent events. Voyager 2's crossing gives us the first direct measurement of how effective this shield really is. Voyager 2 is more than a traveler. It is a roving laboratory equipped to study particles, fields, and waves. Its cameras were turned off long ago to save power, but its other senses remain sharp. Among the most critical, the plasma science instrument, the magnetometer, and the cosmic ray subsystem. PLS measures speed, density, and temperature of plasma, the solar wind, and the interstellar medium. As Voyager 2 approached the heliopause, they watched for the solar wind to slow, then cease. MAG, mounted on a 13-meter boom, measures magnetic field strength and direction, our compass into new magnetic territory. CRS detects high-energy particles from the sun and the galaxy. Leaving the sun's shield should raise galactic cosmic ray counts. Together they would paint an unmistakable picture of crossing into interstellar space. So yeah, those instruments together gave us the proof we needed. On November 5, 2018, after more than 41 years and 18 billion kilometers, the data began to quietly shift. For days, PLS measured hot solar wind particles. Then, in less than a day, those readings dropped to zero. A constant wind suddenly died down, leaving profound stillness. Simultaneously, CRS recorded a sharp, sustained increase in galactic cosmic rays, the smoking gun. The magnetometer showed the field didn't flip but strengthened and stabilized, aligning with the galactic field. 3 signatures formed an airtight case: disappearance of solar plasma, surge in cosmic rays, and a magnetic field shift. The crossing was silent, no crash, no shockwave, no loud event. A serene passage from one state to another, the solar wind's roar faded to the galaxy's steadier hum. A profound discovery made not with a bang, but by patient, quiet observation. Voyager 2 was not the first. Its twin, Voyager 1, crossed on August 25, 2012, giving humanity its first taste of interstellar space. They took different paths, providing unique data points on our heliosphere's shape. Voyager 1's plasma instrument had failed in 1980, so scientists inferred the crossing using other instruments. Voyager 2 arrived with PLS working, a game-changer, directly observing the solar wind's shutdown and interstellar plasma just beyond. Different solar cycle timing likely made Voyager 1's crossing more turbulent and Voyager 2's smoother and more defined. Together they transform a static picture into a dynamic model of our solar system's place in the galaxy. The silent discovery is rich with meaning. Every data point tells a larger story about our sun and the galaxy. With PLS, Voyager 2 confirmed the interstellar plasma is significantly denser and much colder than inside the helio sheath. This constrains the pressure that sets our bubble's size and shape. Magnetic data show galactic field lines draping and compressing against the heliopause, a layered, complex interaction. It reveals how stellar magnetospheres interact with the galactic environment around other stars, too. Voyager 2 measured a sharp rise in galactic cosmic rays, a precise gauge of radiation beyond the sun's protection. We learned the heliosphere blocks about 70% of this radiation. That number informs designs for deep space missions and astronaut health strategies. Ultimately, the data show our system is deeply connected to the Milky Way, a constant handshake of forces. Voyager 2's quiet breakthrough lets us study that handshake, the intricate dance defining our home in the universe. The heliopause is not static, it is a living, breathing surface that changes with the sun's 11-year cycle. At solar maximum, stronger winds push it out. At minimum, the interstellar medium presses it in. Voyager 2 recorded brief forays across a layered, possibly rippled boundary before crossing for good. This dynamism alters how much galactic radiation reaches the planets, a key factor for environments and future explorers. These details feed more accurate models of our evolving cosmic shield. Why do we care about a tiny probe's quiet discovery billions of miles away? Because it is exploration, the essence of who we are. It speaks to the part of us that wonders what's out there. Voyager 2 turns our cosmic backyard into a place we can measure and understand, transforming abstraction into knowledge. Practically, its data are a space weather report from the frontier, guiding safer spacecraft and suit designs. It carries the golden record, a message in a bottle from Earth. Our sounds, our music, our images, built with 1970s technology, it endures, a triumph of humanity, not just one nation. Voyager 2 is an ambassador of Earth, our curiosity, our intelligence, our hope. With persistence, ingenuity, and collaboration, we cross unimaginable voids and bring back answers. The faint signal from Voyager 2 is a beacon of human potential, proof that our journey is far from over. There are more boundaries to cross, more mysteries to solve, more wonders to behold. The universe is waiting.